Hello and welcome to the last lesson in Unit 2, Mechanical Advantage and Efficiency. So today, I want you to be able to identify mechanical advantage in given real-world situations and then be able to calculate the efficiency of it. So a couple of definitions before we get rolling here. There are two types of mechanical advantage. There is actual and then there's ideal. So this is real world. And this is on paper. All right. It's one of those, well, on paper, this is what it should be. So what's the definition? Well, actual mechanical advantage is the ratio of your load force to effort force. So load force to effort force. So, for example, the calculation or formula then for the advantage is actual mechanical advantage, AMA, is equal to your load force divided by your effort force. So there's an equation you want to put on your cheat sheet, and that will calculate your actual mechanical advantage. Definition of ideal: it is the ratio of the effort arm compared to the load arm. So it's theoretically, this is what it should calculate out to be. So ideal mechanical advantage, IMA, is equal to dE over dL. All right. So there are your two formulas, actual and ideal. One deals with forces and the other one deals with arm lengths. So sliding down here, I'm going to extend my page a bit. Comparing actual mechanical advantage to ideal. So for static equilibrium, so that means that nothing on this machine is working, the AMA and the IMA are equal, which would mean that FL from, I'm looking up above, divided by FE is equal to dE over dL. All right, now you don't have to copy this down, but if I do the math cross multiply, FL times DL equals FE times DE. So we've seen this formula before. This is one you were using yesterday when you're calculating forces on levers. Okay, so that's for static equilibrium. That is to keep the balance. So the teeter-totter, keep it balanced, keep the wheelbarrow from falling over. So it makes sense. If there's no motion, those two should be equal. When the components of a machine move, though, IMA is always greater than AMA. And why is that? Well, we know that if I do that comparison above here, DE is my IMA, okay? So it's the ideal. It's greater than FL over FE. Why is that? Because in the real world, we are not 100% efficient. All right? So when you go to lift something, it's supposed to be the word efficient. If you go to lift something, if you grunt or sweat, this is lost energy. That means your body is doing something else other than lifting the object that you're interested in. So as soon as you sweat, as soon as you start grunting, creating sound, what you've done is you've transferred energy to do something else rather than do the job at hand. There is no machine that is 100% efficient. If that was the case, we would be getting some wicked fuel mileage, and we don't get wicked fuel mileage because our cars heat up, our cars make sound and noise. All right, so there is, and they're not perfectly aerodynamic, so there is not 100% efficiency there. So an example. So I got the gory looking human man. Assume that the forearm has a mass of 2 kilograms. So I'm given a mass, M equals 2 kilograms. And it's concentrated at the midpoint. So it just says that's what we're going to go with here. The effort force of the tricep. Okay. So basically we are moving our arm in such a way that the tricep is being used, which means it's on the other side of the fulcrum, which means we are using a first-class lever. The effort force to hold the arm static is 100 newtons, so Fe is 100 newtons, so the effort force. Determine the following. So A, the magnitude of the load force of the forearm due to its own mass. This is just going back to yesterday, okay? This is calculating that ideal relationship between, your effort load, effort distance, and your load force. All right, all that information we know. We know 100. We know DE is, now it's in centimeters. I'm going to convert to meters. So 0.041 equals, I want to know the load force, FL, and I know the distance is 0.2, 20 centimeters, okay, is 0.2 meters. So doing our division, we get 20.5 newtons. All right, so the effort to keep your arm up takes a lot more than the actual load force, and that's because of the length of the handles. The teeter-totter is severely skewed here, a lot shorter distance here than it is from there to there. All right, so therefore 20.5 newtons is the load, so that's the load your arm creates. B part, what is the AMA of the arm? So what's the actual mechanical advantage? So we know from previous slide, AMA is FL over FE. So FL over FE. I'm going to extend my page. So the load force was 20.5. The FE is 100. So we do that quick division. 20.5 divided by 100 is what am I doing? That's embarrassing. 0.205 or 20.5%. So AMA, we can express it as a percentage. So 20.5% efficient, or advantage, mechanical advantage. I'm just going to use MA for mechanical advantage. So 20.5%, not exactly a fantastic ratio there. C part's the magnitude of the load force when you're holding a 5 kilogram ball. Okay, so I'll move over here. So 5 kilogram ball, well, F equals mg from our second unit, first unit, well, first part of this unit. Mass is 5 times 9.81. So we get the added force on that arm is now 49.05 newtons. So when I go to do that calculation again, Fe, DE, FL, DL, we are looking for the magnitude of the load force of the forearm. Oh, I just have to add that on. That works out all right. I don't even have to do that. So you can just, cross that out. We know that the load force just to hold the arm is 20.5 newtons. That's just from our answer from A part. Plus, I guess the hard part of this question was calculating the force to the ball. So now, 5. Now the load applied on your arm is 69.55. So load is now 69.55 newtons. So that answers C part. D part, AMA when you're holding the ball. So what is our actual mechanical advantage? So AMA is FL over FE. So the load force, 69.55, and the effort force, actually, you know what? I did mess up on that previous one. I do apologize. We have to finish it off because that's the load. We need to find our effort force in order to answer D. So I guess technically I did answer C properly here, but I guess down here, I'm making a mess in your note, I know. I apologize for that, but we got to calculate FE in order to do this calculation properly. So we have to do FE DE equals FL DL in order to answer this question. So I need to know FE. The DE again was 0.2, no, 0.041. The load force is now 69.55. We did that right. And it's 0.2, I think it was. So doing that calculation, my FE then is 339.3 newtons. So now your arm, your tricep, has moved from doing 100 newtons of force to doing 339, so it's over tripled it. So now I can return with that number. I just knew when I got to this part of the formula, I don't know my new FE. That's why I knew I had to go somewhere else to find that. So 69.55 divided by 339.3, and I get 0.205, which is 20.5%. So we can see that it hasn't changed. Your mechanical advantage remains the same because it's proportional. All right, so the point of that example is just to show you that if you have a 20% mechanical advantage, it doesn't matter what load you have applied here, it's going to remain 20% mechanical advantage. Some of you will be saying, well, that makes sense. I don't see what the big deal was, but for some of us, we need to see the calculations. All right, so finishing this up, efficiency of machines. So percent efficiency, the formula for your percent efficiency is, I'm just going with what your textbook uses for notation here. You take your AMA, your actual mechanical advantage, divided by your IMA, and you multiply by 100, and that gets you your actual percent efficiency. So my example here, 50 Newton cart is pulled up the ramp with an effort of 25 newtons, raising the cart 1.5 meters from its initial height. Determine the following. So my IMA is equal to, using your formula, DE over DL. And the formula does work for ramps here, because with a ramp, the DE is simply how far you actually pulled it up. So the ramp is 7.5 meters. All right. The load arm is how high you actually raised it. All right. This is length. It's kind of nice when it's the same formula, but you just got to make a notation to remember that relationship right there. And we get that the IMA is a ratio of 5. Okay. B part, we want to find AMA. And that's your F load over your effort force. So we know that the load here was 50 newtons. 50 Newton cart, sorry, 50 Newton cart, that's your effort force, how much it takes to pull it up the ramp, with an effort of 25 Newton. Apologize, I have these upside down. So your load is the 50 newtons, okay? And the effort, and the dead giveaway is right here. I don't know what I was thinking. It said effort force right in the question. It's just me not paying attention. Is 2. So now we can calculate C part, which is our percent efficiency. So our percent efficiency for C part, percent efficiency is your AMA over IMA times 100. 5, oops, better do it right. Really having a hard time here finishing it up here. 2/5 times 100, you get 40%. So therefore, 40% efficient. All right. If you have any questions, just ask in class.